This video will cover some of the Unit 4 practice problems. The first question we'll look at is number 11, where we have a certain skateboard that's being produced, where Q represents the quantity sold, given the price P. So if we change the price, then we change the quantity sold. We're told a few things about that relationship, in particular the function value at some point and the derivative at the same point, and we're asked to interpret that. Well, one of the great guides for these kinds of questions is to look at the units. If we look at what goes into that function, it's a price, and that price is in dollars. What comes out is a quantity sold, and that is in units. And so what we would express for this is, if we set the price to 140, then we're going to sell 15,000 skateboards. What about the derivative? It's a little more subtle, but fortunately it has a very similar framework. Again, the input is a price in dollars, and from that price we get the change in quantity sold. Remember, derivatives are about rate of change. And in units, let's actually express this as words. In units per dollar of the input, so dollar of price. What that means here is when the price is $140, for each dollar we raise the price, that's the per dollar of price, we're going to sell 100 fewer units. So we'd express that in English as, when the skateboards are selling at $140, each increase of $1 in price will reduce the sales by approximately 100 units or 100 skateboards. Now, that property of the derivative being negative and selling fewer skateboards if we increase price is only one ingredient in a business decision. The other side of it is the actual revenue that we earn, because if we're charging more, we might make up that money in a different way, simply by selling fewer units but at a higher cost or higher price. And what we need to study is the trade-off between those two things, the price going up and the quantity sold going down. Which of those has the larger effect? Well, calculus gives us a way to answer that question by looking at the rate of change, not of just the sales, which we know would go down if we increase price, but the actual revenue to the company. If the revenue to the company is given by the number of units sold times the price per unit, which it is, that's the way we combine the price on every unit times how many of them we sell, then we can talk about the derivative of revenue with respect to the change in price. So if we were to change the price, and every derivative can be expressed as that kind of hypothetical, if we can change the price and increase it by $1, how will that affect our revenues? Well, there we're going to take the derivative with respect to P of P times Q. This is a product, so we use the product rule, and P are the same thing, so we get a 1 times the derivative of the first times the second, plus the first times the derivative of the second, which is Q prime. That tidies up to Q plus P times Q prime. With that, we can evaluate it at the price point of 140 when we have all the information, or for which we have all the information. We know that we're looking for Q and the price is 140 plus the $140 per unit times Q prime at 140. So what's the rate of change of our sales or our quantity at price 140? And we fill in the blanks. This is 15,000. We're currently selling 15,000, and we then add 140 times this derivative, and that was the how much do we lose in sales. So one way to capture this again is we're going to, for a $1 increase in price, gain $15,000 in more sales if we just kept the same sales figure, but we're going to be losing some sales, and that's captured here. We're going to be losing 100 sales at $140 each. The net effect of that is to give us 15,000 minus 14,000, or positive 1,000. That's our derivative. On the next slide, we'll take a look at what that actually means. We found that the derivative of revenue with respect to price, when the price is already at $140, was positive 1,000. What are the units of that? Units of the top are dollars of revenue, and in the bottom we have dollars of price. That combination says that for each dollar, for each $1 increase in price, increase, our revenues increase by $1,000. Around, here's the key element, around a P of $140 per unit, per board. What that means is, even though we are going to lose some sales by increasing price, economic theory says we should always lose sales by increasing price, the net revenue to the company is still going to go up because the number of lost sales is going to be overbalanced by the extra income from the higher price. That's why this derivative is positive. If this derivative were negative, it would be the opposite scenario. We'd be losing so many sales that the increase in price would not make up for that loss, and we'd end up making less money if we increase the price. So we should, in this case here, if we're targeting higher revenues, and that's not everybody's goal, but if we're the company and revenue increases what we want, we should increase the price by a small amount. We don't know what happens when we get massive increases in price, but certainly a modest increase above 140 would fit this model here, given our current price point of 140 and how derivatives and rates of change are local phenomena.